there's nothing you've done till then, you've lost that data, right? So this is the kind of metric that we create. And as time goes on, this RUL value goes to 0, and that means it is at failure. So usually it's a little higher, maybe like 20%, and then that is the threshold of failure. Once it crosses that RUL value, maybe like it's like 10 days or so, or 9 days or something, at that point it has failed. So this is kind of like what the industry standard is in terms of formulating these problems as a time series problem. And so we have kind of worked with some features which we have extracted, which are most correlated with failure. And we had some missing values interpolation. We did some linear interpolation, and we also sort of used feature importances back in the day to sort of make this happen. And with that, we isolated a few features which are mostly correlated to failure most of the time, thereby doing what's known as a dimensionality reduction and reducing the the feature space. And then with that, we created what's a simple sequence model, right? Like an encoder decoder LSTM, right? So encoder decoder models are a good starting point because you can learn a sequence and you can also output a sequence, right? So your health logs which are coming in are sequence data. They have, let's say, tons of sensors. Each of the sensors is one time series. So you have time series which are n in numbers stacked on top of each other, and you are sort of feeding that into your machine learning model. And using that, you are supposed to get one long series at the output, which is a sequence of RUL values. At every time step, you have a certain number x, which tells you how long from that timestamp to failure for that device. So this is a perfect model for that. And back in the day, we were using this. This you could easily sort of, and we have sort of extended this to a transform model or even an LLM, but the idea remains the same. So these smart logs are the monitoring and reporting technology, the smart monitoring and reporting technology. That's the industry standard for tracking these health logs, which go into these encoder, and then through context learning goes to the decoder, right? This is your typical encoder decoder learning mechanism. All right, so with that, we perform some walk forward cross validation and look back. This is just strategies we do to sort of optimize our results. From that, we find that tenfold cross validation, just a way of picking the right sequence of data. We find that this is performing better than the others. So we pick that, and this is kind of on the unpoisoned data set. And interestingly, we find that if you look back too much, your predictions worsen. So you have to really stay in the sweet spot where you can choose where the test RMSE for machine learning model is not increasing beyond a certain sort of a budget, right? So we do that as well. And then with that, we go on and train a base model and show that, yes, the test RMSE of the FGSM and BIM attacks on our HDD data for the attack strengths like these. So as the attack strength increases, the model is supposed to perform worse, right? Because the magnitude of the attack is more. So we see that as it goes to the right, the RMSE of that small toy subset of the data, on that, the RMSE values are actually increasing. So that is proof of the fact that it is consistent. And as far as imperceptibility is concerned, if you look at this, you'd be able to see that literally there is no difference in what the RUL values are. Essentially, between the sequence that's falling off of, let's say, a value of 4 to 0, and then for the next sequence 4 to 0, and then so on. This is for each of the instances that's failing. Okay, this is like n number of failure logs that are in here. So if you look at it and you zoom in on it, there's literally no difference between the actual signal and the attacked signals, even with like magnitudes that are really, really high. So this is imperceptible. So we can't figure it out. The machine learning model can. And so that is where we want to sort of use that model to make better choices for us. Okay, so then we come to the first one, which is data augmentation. So we do an adversarial training where we augment the clean data with poisoned examples, right? So we attack the best performing model with some poisoned data, and then we find an optimal mapping such that the augmented data, the machine learning prediction on that is as close to the original augmented prediction as possible. So thereby we kind of make the model a little bit more robust because it's now seen a lot more variation in the data. So it's a little bit more noisy. So when you train on noisy data sets, it's usually a lot more robust. So that's what we observe here as well. And then we target one more thing, and this is where you have inputs, and this is called LPAT, right? This is a separate model, but we'll see some benchmarks of these two together. So inputs going into the ML model, and then an adversary coming into the ML model and trying to poison the gradients in backpropagation in time. So backpropagation is where the updates to the learned weights happen, right, through the gradients, the little changes that perturb the gradient so that the machine learning model learns. So this is where that happens. So then we do that and we try to prove that this is a robust model output. How do we do that? Well, we do a two-pass. We compute the gradients first in every layer, and we update the parameters in the backward pass. So the forward pass, we learn a mapping, which we are supposed to in the usual way, but then we compute the gradients and update the parameters in the backward pass. So we perturb the gradients in each of the network layers through these adversarial attacks. There are two types, discrete and stochastic, right? They have just a little bit of difference in them. One has a random component to it. The other does not have that. The other just has an averaged strength in it. Here, the strength is chosen randomly between start and end. And so your equation essentially guarantees that this is always going to be different from the prior one. Anyway, so this perturbation of the gradients in each of the network layers make sure that before the gradients are passed on to the next layer, we are essentially changing the gradients in a way that the model has to sort of change itself to learn the patterns well. So you are targeting model level fluctuations and deliberately moving learned gradients in a direction that the model has to now adjust itself to learn the actual gradients, right? So this then feeds on to the feed forward process to learn the new mapping. And if you do this backpropagation again on top of this, this proves for a very robust case of model level hardening to learn the actual targets in an adversarial and noisy environment. So this is what we do, right? And this concept is not new. We extended this to time series, right? So this is essentially where we are, and some work had already been done on it in a different context, but we were able to kind of show this at scale. And the results we got are pretty amazing. Like we were able to see that the attack RMSE actually really came down when you're using these discrete and data augmented versions. And so this is pretty good. And this is for FGSM, and this is for your BIM attacks. And keep in mind, this is not even like the entirety of the data that we are working with. This is a very curated subset. And so imagine if the dimensionality increases, the volume of data increases, the failure modes increase. This is going to be even more significant. But already the gains are very high. And so moving on to that, this is what we have. The changes to the percentage decrease in error for the FGSM and BIM attacks do follow the expected trend lines that yes, with the BIM attacks that we see here, these are stronger attacks than the three below the GSMs. So we're going to see more decrease in error in there than really these. So that is kind of expected. And so we see that, and that's verification. And the best case decrease in error is about 95% from where it was when it was adversarially attacked, right? So this is very good in a sense, and it proves the case for model hardening as a robust way of bringing back the efficacy of a model under certain untargeted white box attack environments. So we demonstrated the indiscernible inputs, and then we also looked at the transferability, meaning that we benchmarked on other data sets as well using the same approach. And it seems like the learning really stays as long as the distributions are not wildly different. Okay, so that was case one, where we saw a real world example of failure prediction that could be hijacked, and terrible scenarios can emerge out of it, but there are ways to do predictive AI and adversarial hardening to make that case. Now we're going to go on to sparse attacks, which are a little bit more mathematical. So first we look at indirect attacks. So we want to mislead the prediction of some target time series via perturbations on the other time series. So we have two different time series that one we are going to be perturbing one, and we expect that the other one is going to suffer because of it, right? So this is an indirect attack. And you also have a sparse attack, which these are less perceptible. And so what we want to do is we want to sort of see how that is affected, right? And there's been work on this on data sets like traffic, electricity, taxi, wiki. These are all standard time series benchmarking data sets. And so you'll be able to see here that by disturbing, time series 5, you can indirectly attack time series 1. And so time series 1 in here, which is, your ground truth, which is this one, you only attack your this green one, which is the PS5. And this is your clean prediction. Your PS5 is going to suffer because of it. So this is essentially what we are setting out to do here. The idea is that you want to induce some minimal perturbations to an auxiliary time series so that the forecast of a different time series is maximally disrupted. So we assume a learned forecasting model like this. So X is of course your input, it's a multivariate time series, and Y hat is your predicted values of the time series, right? So this is what we have for the edge steps or something. And this is the learn function, the forecasting model. It could be a transformer, it could be an LSTM, whatever, right? So this is what we have. And now we want to sort of work with this. So we create the threat model and the attack setting. So what we have in here is basically some sort of a delta where we have the perturbed adversarial input, right? This is only on selected series, meaning on one time series data, we have the adversarial input and not on the others. This is your expert, right? And then X auth is the authentic original unperturbed input. So the residual between that is delta, right? This is your perturbation. And you want to constrain this such that the only elements in series J are modified. So one of the series among them, not all of them. Okay, so this is your premise. And then you want to maximize the error in that prediction subject to a sparsity constraint. So this is just your usual error sort of maximization logic here. So you can only modify a few values in one of the time series over a selected time range, but you aim to disrupt the model's prediction of another time series. Okay, it's a different time series that you want to impact through your perturbation of another time series. So this is your loss function, and then essentially you have a sparsity budget in the kappa, how many perturbations are allowed to do this, and then you can support some non-zero indices. There's some sparsity metric here as well that forces that. Okay, so that's your optimization objective. And now you use a relaxed optimization, which is a gradient-based one, and we transform this space into an L1 or an L2 norm residual, meaning we don't want to work with L0 or L0, which is pretty hard to do. So we kind of simplify the problem and we work in L1 space or L2 space, right? So this is what we have. And epsilon, of course, is your attack strength. And you have a binary mask ensuring only that time series J is perturbed, okay? So this kind of applies to the data and makes sure that one of the time series data is perturbed and not the other one. All right, with that in mind, we can do gradient ascent on top of it. Gradient ascent is like the opposite of gradient descent, right? It's more of unlearning at play. So after every step, you can project your delta back onto the constraint set. So this is what we have. We clip by norm the delta of the Piet norm of the delta below a certain threshold of epsilon, right? And this is your attack strength, right? So and through this, your delta that emerges out of it is a clipped version of what it could be. And therefore, you can put some changes in it in the reverse direction. And you can also modify how much of a change you want it to be. So it's essentially you're moving against the flow of gradients. All right. So there's been some work on randomized smoothing defenses to actually defend against something like this. And randomized smoothing is actually pretty crazy. It's you add Gaussian noise to the input and you take the expected prediction, making the model more robust to small adversarial changes. This is what we do, right? So we are, sort of, instead of forecasting from X, we forecast from multiple noisy versions of X, really. And this reduces the sensitivity to small adversarial changes in any one part of X. So that's what we are going for, right? So giving the probability that the smooth forecast stays below the threshold R element wise. And this has been around for a long time, but just in different contexts, right? So now we use this here. And there's been some work actually, and we've gotten some pretty crazy results, but there's been some work before that which also hints at this being really a very good defense mechanism. And another defense that I'll take a look at is the minimax sparse layer defense. And this one is interesting in that it is end-to-end sort of trainable as a defense. And it simulates adversarial noise using a differentiable sparse perturbation generator. So you have a perturbation generator here, and this you basically what you have is a min-max objective that you are trying to sort of work with. So your model tries to maximize the prediction performance on the perturbed inputs, and you have a generator which is phi trying to simulate the perturbations that make the predictions actually worse. So it's more like, you have a tussle going on, right? So the loss terms, if you really look at it, you have a log likelihood in here, and basically, you have a ground truth, of the future values under the forecast that is made from the perturbed input, right? And so there are a couple of different types of losses that we'll take a look at. One of them is going to be a generator loss, right? This generator loss measures how badly the prediction deviates from the ground truth due to simulated noise. Okay, so it generates and kind of measures that. So a high value of this generator loss means that the perturbation generator was effective at fooling the model. So if your prediction under influence is very, very, way off charts when you compare it to your original one, then the generator did a good job of fooling it, right? And so you also have the predictor loss, really. And the predictor loss is basically the log likelihood again of the ground truth future values Z under a forecast made from the perturbed input X plus delta here, right? So this is again log likelihood. And so a high LP value here means that the good forecasting performance has been achieved even under noise. Okay, so you have a couple of loops, right? So you have an outer loop and you have an inner loop in this sort of thing. You minimize one with respect to phi, so your adversary finds perturbations that most degrade accuracy, and then the model learns to make accurate predictions under perturbed inputs. This is what we're going for. And then with that, the results are striking in the sense that it does seem like the minimax defenses and the randomized smoothing are pretty good, actually. So this kind of shows you that the deep VAR attack that we tested on, and there's some work before us that tested it as well, and we did some follow-up, but that has been tested, actually sort of did transfer over very, very well. And so your departures, the attack transferred from deep AR onto this time series, this new time series is actually pretty good, meaning that this time series, the value of TS1 actually really sort of is affected by your experimentation on TS5. So that's interesting because it proves transferability in a sense of the attacks on one data and then kind of looking at that from another data which has not been perturbed. And so the takeaways are that sparse and indirect attacks are very effective and become more effective as the kappa increases. And probabilistic attacks are more effective than deterministic ones, specifically for small kappas. Also that randomized smoothing and minimax are really robust, more so than data augmentation. And this is the really interesting part, that during transfer, attacks on multivariate time series are more effective than on univariate ones, about 3 times more effective on multivariate ones than on univariate ones. response. Again, is because of the state space explosion, but again, that is something that has been observed. Okay, moving on to like a really cool insight about how moving target defense actually plays into this picture. We want to combine the randomness of this technique called moving target defense and model compression to build a more robust and deployable defense, because attacks threaten the reliability of machine learning models in safety critical domains, right? So we want generalizable defenses for both classification and forecasting, and we want to build lightweight defenses. So MTD is a strategy to increase the unpredictability for attackers. So your traditional ML models, the attack surface remains very static, making it easier to probe and exploit. In ML, this kind of means that if you dynamically change the model or its parameters during inference, well, then there is an opening there that you can exploit and kind of make it more robust. Okay? So this unpredictability makes it significantly harder for attackers to succeed and significantly boosts robustness. So you change yourself as the environment changes. That's the motto. And MTD makes attacking harder, costlier, and less reliable, thereby raising the bar for adversaries, right? So this is what we are going for. So we'll see how that is done, but there's been a fair amount of work that has been done back in the day, and there's some work that's going on now as well. There's some opportunities here. So most prior work has focused on classification tasks only. There have been very few attempts to apply MTD to time series regression, and there's been no exploration of quantized MTD defenses as well. So we went ahead and did some regression support on it, and we also did some quantized defense evaluation as it, on top of it to close those gaps. And the Morphins framework, if you look at it, well, it's just a combination of a few things. You have a strong base model, and you generate student models from it using Gaussian weight distributions and train each student to ensure individual robustness. And then you randomly pick a student at inference time. So the intuition is model level diversity leads to better defenses. That's what we're going for. And this is what it looks like. So you have some, sort of like base model. And from that, you have student models. And all of these are a little different from each other. So you can retrain each of them. And these will actually give you very accurate and diverse pool of student models that will then take on parts of the data themselves through adversarial training, and gives you a very diverse sort of a landscape which is robust against adversarial inputs. And then when the adversary comes in and tries to poison the input and goes through that, well, then the output is sort of a lot better than if that defense was not there. So this is what we are sort of probing right now. The advantage is that the models share basic structures. So every student model does not need to be trained from scratch. Very small perturbations will suffice. Each student is adversarially trained against different attacks, enabling collective defenses. Unlike traditional ensembles, this is very lightweight and very resource efficient. So you also add this unpredictability because of the randomization of each model. So your attacks are less effective, essentially. And this is not just confined to image processing or even classification. It's really generalizable. And that was one of the gaps which we went ahead and filled. And this flexibility we leverage to apply it to PSF on the edge. So we also did some quantization and adversarial training. We threw that in the mix, and we validated that in terms of latency and reduction in model size and what the end results are. So then what we found is that it's pretty good. We replicated that benchmark on image data first, and then we extended to time series benchmarks as well. And we applied post-training quantization and analyzed the trade-offs in performance, robustness, and size. And we found that very early positive results are coming out of it, about 30 to 40 to 50% reduction in the delta, and consistently improved robustness across all data benchmarks, especially under the untargeted white box attacks. The randomized inference actually helped the effectiveness, and also PTQ, which is quantization after you have trained the model. It reduced model size by 40 to 70%. That's a big win, because if you want to deploy machine learning models at the edge, you need lightweight models that perform well. And so these quantized models actually demonstrated very strong resilience, retained their adversarial robustness despite significant compression. That's pretty good. And now we're also looking at quantization aware training. That is, you're training and you're quantizing at the same time. We're looking at stronger threat models and adaptive inference as well. Okay, last use case. This is dynamic attention. And in here, you have a transformer. All of us are familiar with the transformer architecture, the encoder and decoder, right? We have input embeddings, positional encodings, encoder, decoder, output, blah, right? So, and then this is better than RNNs and listings because you have parallelization, better long-range modeling, scalability, etc., right? This is kind of the de facto thing that we do, use the attention mechanism, but they are vulnerable, the architecture itself, because you have fixed activation patterns. You also have sensitivity to token importance, right? So your attention map, if we look at it, there are parts of it that can be hijacked and said, okay, if I just change things here, the whole prediction model falls apart. So we wanted to sort of look at what that is and how that can be worked on. So there's been prior work on it as well, a little bit, but we really kind of picked up our own work in 2024 and tried to sort of see how we can make this more resilient. So we looked at dynamic attention, again, kind of brought introduced by Shen et al. But we were looking at token selection and dynamic masking to make this happen. So what we did is we went ahead and looked at the standard transformer, where attention is computed like this, right? It's a soft dictionary lookup. But then we went ahead and said, okay, instead of that, can we actually sort of do something different, right? Like in the dynamic attention, we compute original attention weights and then aggregate the token saliences from that. So this measures how much token I attends to all other tokens across all the heads of the transformer. And if you have a higher SI, it is, it means more salient token, right? Those are the ones that are more important. And then we rank these tokens by salience, and then we apply attention rectification. So this rectification boosts attention to high salience tokens using a multiplier that we have, beta multiplier, which is greater than 1, and keeps the others unchanged. That's the whole thing. You kind of find out the ones that are most important, and you work with them. Those are the ones that you want to harden. This helps reduce top token sensitivity, helps distribute focus under attack and perturbation, and early results on time series benchmark show very, very encouraging prediction performance without any additional compute burden. The key finding here is that the error AUC in a dynamic attention transformer is less than the error AUC of a vanilla attention transformer for all attacks at all epsilon levels so far that we have tested. So this is really key. So that's where we stop here, right? And now I want to talk about just a little bit about the attack surface on the LLMs before I take questions. So if you look at the attack surface for the LLMs, you have prompt levels, you have model level, you have training data attacks, you have API or deployment level attacks. There's a lot of vulnerabilities. You could do prompt injection, you could do jailbreaking, right? You can manipulate the input without access to the model internals, right? At the prompt level. If you look at the model level, we've been looking at some of it. We target the model's architecture, weights, and training behavior as well. Could be like backdoor Trojan attacks, could be gradient-based attacks. We looked at one. Could be malicious fine-tuning at the end using like LoRa or QLoRa, right? So we can inject harmful behaviors in the adapter stage of fine-tuning. You do catastrophic forgetting or unlearning, right? You can make the model forget specific knowledge. You can also attack the training data through poisoning or membership inference attacks. And then when it's deployed, you can do model stealing. You could also sort of change the reward model in a reinforcement learning through human feedback, reverse engineer the reward model, right? So these are all avenues that are being actively researched on right now. And the trade-offs between all of these, right, the attributes of trustworthy AI really essentially is you have this Pareto surface, right? So your adversarial robustness and accuracy essentially follows something like this. You have a Pareto front and you want to be in the Pareto improvement lines and the feasible regions where your accuracy is good, but because of the adversarial robustness, your you want to make sure that you're in a sweet spot. For those of us who have worked with multi-objective optimization, it's kind of like a similar thing, except that here you have to lose some performance guarantees, and you have to certify these attacks on top as well. These defenses essentially on top. So this is where we want to be. And really, the taxonomy of attacks on GenAI models are really related to like availability, integrity, misuse, model privacy, right? There's way too much that's going on as these models become a trillion token, and you have small language models that come out of it. Essentially, if you have attacks that are on these larger models which feed into these smaller models, then the smaller models inherit that So target tracking is very important, but these are all of the areas that work is going on in. And so some of the dominant generative AI use cases are in code generation and support chatbots and enterprise search, and of course like agentic that's going on right now. But across all of these verticals, you will find adversarial AI sort of being a centerpiece of development research in the next decade or so. It's already kicking up, and it's going to be even more so. So, according to NIST, the existence of simultaneous attacks on multimodal models suggests that mitigation techniques that only rely on single modality perturbations are not likely to be robust. So, we are having to look at pretty much everything, all of the avenues to sort of harden this as we go forward. So, that is where we are at, and this kind of opens up the pathway for a lot of people to get involved because there's a lot of opportunity that will open up in cybersecurity and um, uh, in large language modeling as we go into the future. So that's where we are, right? And so this is kind of bringing us to the end of this talk. I guess I can take some questions now if you guys want, and then like we can sort of go from there. Thank you.
Thank you so much, sir, for such thought-provoking, insightful session. We are now open the floor for the questions for the audience. If you have any questions for the speaker, please feel free to raise your hand or type them in the chat.
Yeah, myself, Dr. Madhubala. I'm PA of the project on digital twin creation. So here my question is, how digital twins are used to quantify the resilience of cyber physical systems?
Yeah, great question. So I think across the board you'll find that um, regardless of the type of signal that you have, there are always mathematical formulas and transformations that you can create to uh, create a resultant signal that is sort of obfuscated. And really, the key goal here is to certify the level of defense that you have. What are the provable guarantees that you can uh, that you can impose that the model will be able to defend against it and with a certain confidence. Now, if the environment changes, then it is a very difficult task. So, what we are having to resort to is changing the model's ecosystem itself so that there is some layer of uncertainty for the attacker as well. So that is where I think a lot of work is going on, but it's all still a mix, and I think there's a lot of more work that needs to be done on that end. But thank you for that question.
Yeah, thank you.
What's the use of novel optimization usage on optimization?
Yeah, I think optimization is very important because let's say you have a lot of things to choose from, right? It could be any problem, any engineering problem, and here you can also kind of make this a search problem, meaning that what are the right model parameters and right model architecture choices that will give you the best defense. So there can be many choices, and among them, some of some of these are going to be good. So you need optimization algorithms which will cut through the noise, choose the right states, do it rather fast, and give you something that is statistically significant, meaning that if you run it 30 times, well, you are going to get something that is not due to chance. A lot of the algorithms, when we see them, if they are heuristics, there has to be some very carefully crafted experiments to prove that they are not random or the results are not random. Rather, the results are actually grounded in statistics and grounded in some actual signal that it is following. It's like vaccine development, really. You follow like a very curated set of clinical trials to prove that the effect of that is actually due to something in the vaccine and not due to chance, right? So similarly, an optimization algorithm can give you good results on objective functions by chance or by tuning the hyperparameters in a way that makes it look like it's good. But if you look at the no free lunch theorem, there really is no one algorithm that will give you really good results on all sorts of problems. It's actually problem dependent and field niche dependent. So what we do is we come up with these novel approaches for a certain subset, for a subset of problems, and try to make sure that those results in the purview of those distributions are actually causal and not due to chance. Okay, so I think that that is where a lot of work has gone on. Also, you'll find a ton of algorithms out there, but if you have enough compute, the problem becomes a lot easier. Um, Back in the day, compute used to be an issue, and so people used to work a lot with intelligent optimization algorithms. But the problem really remains at scale as well. As you scale things up, the state space and the curse of dimensionality also kicks into the picture, right? But that's a great question. I think choosing the right algorithm makes a lot of difference also. Yeah, thank you.
Thank you so much, sir, for such thought provoking and insightful session. Your keynote on traditional shifting landscapes of quantifying risk, reliability, and resilience for cyber physical systems in the generative AI era was truly enriching. The way you connected machine learning, nature inspired computing, and real world applications in cyber physical systems was both eye opening and intellectually stimulating. Your expertise and research contributions in the evolving field has left us inspired and curious to explore further. We are truly grateful for your valuable time and presence, even virtually. We look forward to learning more and more for your work in the future. Thank you once again, sir.
Thank you. It's a pleasure.
We'll be starting the next session in within few minutes. Guys, we have one more session. It is from Dr. U. Srinivasul Reddy, sir. So please stay back. The keynote is in on AI in action, real world applications for engineers. Good morning, sir. Am I audible to you?
Yes, sir. Good morning, sir.
Start. Good morning to one and all present here. We now move forward to our next keynote session of the day. It gives me immense pleasure to introduce our keynote speaker, Dr. U. Srinivasula Reddy. Dr. U. Srinivasula is an associate professor in the Department of Computer Applications at the National Institute of Technology, Tiruchirappalli, where he also leads the Machine Learning and Data Analytics Lab. He is a core team member of the Center of Excellence in Artificial Intelligence established at NIT in 2020. Dr. Reddy began his teaching career in 2003 and he joined NIT as a faculty in 2008 after completing his PhD in 2013. His research applies AI and deep learning models to real world societal domains such as agricultural, bioinformatics, banking, telecom, and healthcare. His lab has guided over 12 doctorate scholars, 10 plus postgraduates each year, producing impactful results in practical machine learning applications. He has published more than 64 research articles, 4 book chapters, and has received multiple awards, including the Best Research Award 2018, the Best Performer Award for 3 consecutive years from NIT. He's also earned Best 2 Paper Awards in IEEE international conferences. He was recently recognized among the world top 2% scientists for 2023 by Elsevier and Stanford University for contributions in AI and image processing. Dr. Reddy has delivered over 50 invited talks at national and international platforms and has conducted numerous conferences, workshops, and training sessions. He also secured research grants worth 127 lakhs from prestigious agencies like ISRO, DRDO, DST, and DIT. He is also a member of CSI and also affiliated with ACM, IEEE, and the Analytical Society of India. He will be delivering his keynote talk titled AI in Action Real World Applications for Engineers. Although he is joining us virtually today, we are truly privileged to have him share his insight. Please join me in warmly welcoming Dr. U. Srinivasula Reddy.
Sir, good morning. You are able to hear and see my slides?
Yes, sir, we are able to see your screen.
Sir?
Yes, sir.
Yeah.
Yes, sir, we are able to see.
So, thanks for the invitation. And yeah. Thanks for the invitation. And I would like to thank the organizers who are inviting me for a keynote session in the international conference. A special thanks to Brahmanandam Reddy sir. He has associated with me for past 10 years. Okay, I was associated with this international conference for past few years, right? And as a session chair, a technical session and all. Today I'm happy to be here to give a keynote lecture on AI in actions and real world applications for engineers. So already we are in an era of AI. Everyone has an fond of AI, artificial intelligence. What is that AI? How it will be in a reality nowadays? How we are applying for the real world applications or real world problems? So what exactly AI means? Where these concepts, right? How these concepts has come into actions in a nowadays? So that is a very important area. Now all the colleges across the globe, now they are starting AI and ML and AI in data science, AI in cyber security, AI in agriculture, AI in biomedical, AI in transportation, all places now we are using artificial intelligence. Already it has come into reality. In many places we are using. Even now if in our mobile we are using AI and with the chat GPT, right? In a generative AI, okay, we are using, right? So now see this. What is the first before getting to AI? See what is the artificial intelligence. This today I am going to elaborate or maybe give a glimpse of artificial intelligence, machine learning, deep learning, and generative AI, and some of the real world applications. So what exactly AI, if you want to expert in a generative AI, first you should understand what is AI. What is the introduction to AI and machine learning is a subset of AI. Then deep learning, introduction to generative AI, large language models, prompt engineering. Nowadays, everyone has giving lot of importance for prompt engineering. Where exactly prompt has coming? Where how do you can interact with your chat GPT? How do you interact with your AI models? That where this prompt engineering. See, AI is highly paid job nowadays. What is that exactly? Now, how you can create the prompts? That means how intelligently you interact with your chat GPT models or generative AI models. Then ethical consideration, challenges and limitations, and all these things. Okay. Now let me start with an AI. Then we'll go to the generative AI. We'll go in this path. Introduction to AI, then machine learning, then deep learning, then generative AI, some of the applications again. Okay, now what exactly AI, where we got these concepts? What exactly AI, where we got this? See, first one, this one, right? We were mimicking the human five senses, the sensing organs which is available in human, right? What innovation happened through this? This is a visual, right? Vision based sensors. So with through human eyes, whether cameras, whether your camera is able to see nowadays, yes. So which innovation happened? The computer vision, computer vision based on human visions, they developed a computer vision. This is the future of artificial intelligence. Computer vision is the future of artificial intelligence. For example, you take a Google map. How Google map is working? Google map is working based on GPS and a global positioning system. We have a source and we have a destination. We'll go and we'll see how we are reaching the destination. Same this Google map, whatever the Google map, what we are nowadays, it is working based on GPS. Now it is moving from GPS to same Google map. If you open now what we can see, we can visualize the streets, visualize the buildings, visualize anything. That we call as a VPS, visual positioning system. So what is the, where this it got from this computer vision only. So now see every building you can see the pedestals, we can see the street views, all the things we can visualize based on the basic sense, your human eye. From that this now autonomous vehicles, drones, all your remote sensing, or even in your toll gate, fast tag, that and all working based on these visual systems only. So first, where do you got that intelligence? First sense is human eyes. Similarly for ears, Siri, Alexa and all, touch screen. Now see this sense. Where what is intelligent we have? Now this is a smell based gas sensors, electrochemical gas sensors, all these things. So from this they developed a concept called as e-nose. What is that e-nose? Electronic nose. What is this electronic nose? What is the purpose of this electronic nose? To predict whether this, whatever that now everyone nowadays we are all depending on the packed food. Even you, for example, you take a milk and it is coming in a packet. How do you check that milk is fresh or not? So that based on the smell only we are able to detect whether the milk is fresh or not. That can be detected by this electronic nose, electrochemical biosensor. How do you detect whether the meat is fresh or not? Whether the packed food is fresh or not? That can be detected through electronic nose. So lot of applications. Even how do you check the quality of coffee seeds? Coffee seeds, because now coffee quality grading they have to give. First grade coffee seed, second grade, third grade and all. So that coffee grading can be done based on the smell. So that now you can use this electronic nose to make the coffee beans, coffee seed grading. And also we can, now how do you check whether human, any human is healthy or not? Based on the smell it is coming out of his mouth. So based on that, previously doctors are asking, open your mouth. Why they are asking? How much is person get affected with that? So because of, by checking that smell, you can detect how he is affected. That can be detected by this electronic nose. Even plant is healthy or not. The healthy plant will produce a good smell, and diseased plant will produce a bad smell. How do you differentiate that one? We have one compound called VOC, volatile organic compound. Okay, based on this we can we can detect whether the plant is healthy or not. Like that, so many applications are there in this electronic nose. Similarly, we have e-tongue. What is that e-tongue? Electronic tongue. If you lost taste bud, that we can use it. So these five senses are already there with us, already there in this. Okay, now what people are doing, they're mimicking these five senses, what is naturally available with us, and developing artificial systems, artificial intelligent systems. So that we call as an artificial intelligence. Now you tell me, what is the definition for artificial intelligence? Making intelligent missions. Making intelligent mission, or man-made intelligent is nothing but artificial. Man-made intelligent is nothing but a artificial intelligence. How do you make these intelligent systems? Where do you got that intelligence? So for example, in five senses, our eye, if you go to new place, automatically your eye will captures all the surrounding view, right? Similarly, now computer vision is doing like that. Now crowd sensing, if any abnormal behavior is happened in a crowd sensing, in a shopping mall or a railway station or airport and all, so your model will automatically is detecting that person behavior. Based on that, it will indicate and give the alert to the system. So that is already in action. Your AI is already in action in many places. Based on that, we are even in online classes, if we are all people are open your cameras, so based on your facial expressions, we can detect. We developed one beautiful just now we completed one project, AI assistant system for astronauts, for ISRO astronauts who are flying on the right, and the space. So for them, what is their feelings, what is their emotions, what are their facial expressions? So through computer vision only, we are able to detect their emotions, feelings and all. So that is an already in reality. Now we are testing our model in a Tirunananthapuram in Kerala for astronauts. So that is even in a many manufacturing industry, that vision based sensors are using to detect whether it is packing is properly done or not, and doing lot of inspection. And for example, fortune oil, the cap is properly placed or not, any leak is there, any crack is there, that can be detected. Like that, so many applications are there in it. So now whatever we have by naturally, that we are mimicking and making artificial. What are the different stages and types of AI? Now that we have three types. One is a narrow AI, second one is the general AI, third one is a super AI. What is a narrow AI? We are still here only, dedicated for one task. Now we are moving from this general AI, perform like human. How human is performing, like that. This is the general AI. What is the next level is super AI. Now people are trying to, everyone or your models or devices to be a super AI. That means intelligent than human. So we got intelligent from the human senses. Now the people are going behind our level, that is super AI, right? But still we are in here. And now see this slide. Now we are in AI as introduced in 1950s. Now now we are in the year of 2025. Now what was there to come up to this level? Now only we are more fond of AI. How we have different type of AI. Generative AI is there, agentic AI is there, and the explainable AI is there. Like that, so many AI concepts has come. Now which is AI is an a part and participle of all our activities, day-to-day activities in all domains, across the domains. Now they're extensively used AI. Now why this has taken this many years now to come and to be popular and to be useful? Now what make AI to be adaptable nowadays? Because of the GPU. Because of GPU. What is GPU? Previously, we had a limited computing powers. All our models, traditional models, are using CPU. What is that CPU? Central processing unit. It has limited computing power. For example, easy to understand is when we are in childhood and all, that weather prediction. So we cannot predict correctly, accurately, because we have less computing power. Now, this computing power has been tremendously increased, are available in terms of GPU. What is there inside the GPU, graphical processing unit? Inherently, it has massive parallelism. GPU has inherently massive parallelism. That's why your all AI deep learning models become so popular. Now, what is the problem with this GPU? GPU, you want to train because of the GPU, your this deep learning becomes so popular. Okay. Now, what is the problem with this? Now, you want to train this deep learning models. It takes longer time to train. Longer time, maybe there now some weeks or months to train. So now, how do you reduce the time? Now we have moved from CPU to GPU. Now they are moving from GPU to other processor we call QPU. What is this QPU? Quantum processing unit. Now that quantum processing unit, quantum has it has a qubit concept and superposition. Because of that, speed is being increased so that we can reduce the training time in deep learning models. Now people are learning quantum AI. Now AI to quantum AI. In that quantum AI, again they have quantum machine learning. Okay, QML. These are now concepts. There they are using this processor, but this yet to come into market. Maybe 2026 or 2027, there now IBM and other companies, Google, everyone is trying, but simulators only. But they have to compute this quantum process. Because of these things, these innovations happen. This because we have computing power is available in terms of GPU, NVIDIA cards, Jetson Nano, all that different cards. Okay, we are getting computing power, so deep learning becomes so powerful. So now what was the first approach in the 1950s? What is the disadvantage of that? That we'll see nowadays. Now, AI has three approaches. Artificial intelligence has three approaches. What was the first approach is expert-based approach, expert system-based approach. Second approach is intelligent-based approach, intelligent-based. Third approach is learning-based approach. That we are going to see today. Okay, how do you define he is an expert in a particular field? He has in-depth, wider knowledge in a particular domain. But now all these expert system works based on rule based. So in the domain, if you take any domain or any real world problems, what is happening in nowadays? All your real world problems not in the form of static. 80 to 90% of your domain or your problems are dynamic in nature. So writing it or devising a rules for dynamic system is very, very tedious. Whereas in static system, very easy. Unfortunately, all our real world problems dynamic in nature. That's why this expert based system has limited applications. Okay, so this even though this was the first approach in AI, but why it has been limited? Because your system in your models or your problems are dynamic in nature. Okay, now people moved into the second approach. What is second approach? Intelligent based approach. What is this intelligent based approach? What is the first one we see? This is the first intelligent approach. base for all your deep learning and everyone. So human brain, inside human brain, what is there? Neurons. How many neurons are there? Millions of neurons are there. All are connected or not connected. Every neuron is connected with other neurons. That neural network, they call it as a neural network. What do you mean by network? Exchange of information between two nodes or two devices. Here, exchange of information between two neurons or any neurons. Where this intelligence? How I'm asking one question, you are responding. Are you reaching that? Okay. So based on this intelligent system, they developed the first intelligent model is called as an artificial neural network. Now you might have got the definition. This neural network we have naturally, they mimicked the working function of this one. Now they're making artificial neural network. When this artificial neural network, okay, what is there is in a system. Any system has three things: input and process and output, right? So now this is a layered approach: input layer, right, output layer, and it is not a process layer, it is in a hidden layer. Now see this. Now we have a input x1, x2 up to so on xn. Okay, these are the inputs. Now you will take that inputs and process in a hidden layer. Okay, then you will get an output. What is that output? Is y. Okay. Now when we ask question, we immediately will not respond. We will, for each question we will assign some value. That is called as weights. That we call as a weight. Okay, these weights now up to wn. So then summation of this one. Then we have an y equal to this. We can write x1 into w1, x1 into w1, and so on, x2 into w2, w1. Okay, then x2 into w2, like that we can write. Okay, equation. But what is happening? This always this y prediction is controlled by something that we call as an activation function. Activation function is to, the purpose of activation function is to introduce non-linearity into your system. Okay, non-linearity into your system. Here that same answer you know, but you will not open your mouth because it's something you are controlling. So that is an activation, because we have different activation function. Tan H activation, sigmoid activation, and Rayleigh activation if you go, right? So now if this summation will get into this, is that means that every time you will get a correct answer, immediately you will get a correct answer, you will not get a correct answer. So that difference is nothing but a error. What is this error? Your actual y minus whatever predicted y cap. This we call as a difference is called as an error. Now you have to reduce this error. Okay, how do you reduce this error? In a MLP, we have not a single hidden layer. If you have multiple layers, then we'll go back. For example, you tell one answer. If I say this answer is not correct, then what you try to do, you will reprocess, will rethink. Again, you go back, think that same procedure, back propagation. It will be used in a multi-layer perceptron. What is the another algorithm is there is gradient descent. For example, gradient perceptron. Okay, when do you use single layer perceptron? When do you use multi-layer perceptron? What is a perceptron? Perceptron is a simple neuron in any network. So how do you measure is the person is intelligent? The intelligence can be measured through IQs. What is that IQ? Intellectual quotient. You have an intellectual quotient. If you observe in your classroom, you have 50 to 60. All person may not have the same IQ, even though they are in same environment and same subjects they are studying. Why? How this IQ is differ from person to person? Because the way of perception, the way of perceiving the things from person to person is different. I'll repeat, the way of perceiving person to person is different in their intelligence. Because if you take an example, Einstein, right? Or maybe who found out that gravitational force, right? So that how he perceived things, how scientists, how they develop the models, the way they perceive the problem is different from person to person. That's why the IQ also changes. This same P is here. Single layer perceptron, multi-layer perceptron. When your data, when your problem is of linearly separable. What is the linearly separable? Your class can be separated by single line. This is a one class, maybe plus and one class, minus minus another class. You are able to separate your classes with a single line that we call as a single layer perceptron. You are not able to sub single class. For example, now I have plus, then plus, minus, then plus. So this plus, this you cannot separate with a single line, because here you draw single line, here you have to draw it. Okay, then these kind of problems, if you have non-linearly separable, that means you are not able to linearly separable. Okay, that time you use a multi-layer perceptron. Example for this is AND gate and OR gate. AND gate and OR gate, you can try it. Not that one. Here, this example is XOR gate. So you want to know when to use this ANN, or whether you have to use single layer perceptron, multi-layer perceptron. This is the first intelligent approach. What is second intelligent approach? You see this. Based on this Darwin theory, evolutionary theory aspect. So what is the basic entity here? Here the basic entity is a neuron. What is an evolutionary basic entity? Is a gene. Survival of fittest. Survival of fittest. When you stretch the chromosome, you will get a DNA. Entire DNA is not a gene, only segment which has the ability to produce the protein. That we call as a gene. So now, see this. Based on the intelligence of neural network, they develop this one. Now, this based on the gene, survival of fittest. So based on that intelligent, people developed another beautiful technique called as a genetic algorithms. Okay, these are an intelligent approach. Now you see this another intelligent approach, particle swarm optimization. What is a particle here? Either birds or fishes. Based on this behavior, you see the morning times and evening times, birds are flocking. How birds are flocking? All in U shape it will go. There is no leader. But what for they doing? So that group is nothing but a swarm. What for they doing? What they trying to do here? There is no collision happened. But what is this one? Optimization is nothing but either to minimize your objective function, or maximize your objective. Minimize or maximize. If take these birds, what to minimize these birds? It has to minimize the distance travel. How much distance it has to travel. Okay, then what it has to maximize? Food. What is the food? How much food? Right? The food. These birds are moving for food only, to fetch the food. So now the food has to maximize. The distance should be minimized. That's why they call it as an optimization, right? So now particle swarm optimization is one of the global optimization technique. Global optimization technique. What is that global optimization? This optimization is nothing but either to minimize or maximize your objective function. Either to minimize or maximize your objective function or your fitness function, whatever it may be, right? That is optimization. Now what these birds always were very intelligent. How they are intelligent? They'll always find the shortest distance or minimum distance and always find the maximum food. If any bird see or food is available, suddenly they will turn like this. Okay, that intelligence where they got it. There is no leader for each birds. Okay, in fish schooling also, but they have in a global based, local based and all. Okay, then these model always gives the global best. What is that global best? For example, you take this scenario, we have like this. Okay. Now what we can do, we have local, we have like this. For, for, for this interval, this is a local. What is the here local minima, here local maxima? If you take here, this is a local minima, this is a local maximum, right? So if you take this is a local maximum and local minimum, you can here, then local minimum and right local maximum. Now among this, which has the local maximum among this, like this may be the, if we take this one, this will be the your local or global maximum. So this algorithm always gives the global best solution. Global best solution always gives the global best solution. Yeah, it will never ever struck with the local minima or local maxima. That's why it is called as a global optimization technique. Not only this, see this, another one. Ant is the smallest creature, but it has an always intelligent. So many people are compared with the ant with the human. Human is intelligent or ant intelligent. So ant is always find the saddest path. Even if ants are going in some places, now we will do some kind of this. Okay, what we'll do? If we go like this, ants, you will put some obstacle or maybe one stick here in between. So ants randomly will move in this place and also this place. But after some time, it always find the saddest path. How they know? Who taught that? So ants will, while moving ants, they'll release some pheromone. That pheromone evaporation rate theta it has. So these two algorithms are called as a global optimization. These two algorithms are called swarm intelligent techniques because you see, so AI is a set, okay, in that subset is CA, computational intelligence. In that computational intelligence, subset is SI, swarm intelligence. So like that, so many algorithms are there. All they inspired from the biology. That's why these algorithms are called bio-inspired algorithms. These algorithms are called meta-heuristic algorithms. These algorithms are called nature computing algorithms. All are the same. Okay. Now see the last one. Now this will work based on the human brain, whether it is a fuzzy in nature or not. Okay. What is the fuzzy set? Now there are two sets. One is this one is crisp set. This one is fuzzy set. Okay. In between this, if you take this set either 0 or 1, but if you take this set, will take integral 0 to 1. We have infinite numbers from between 0 to 1. So now we'll take a fuzzy membership and do this. This fuzzy membership, whichever has a higher side or lower side, and it will go. Right? They have different fuzzy membership functions. Now this we call as a soft computing technique because it will deal with the precise, unprecise, unambiguity, uncertainty. But all your AI models comes under soft computing techniques only. This approach, whatever we discussed so far, one is AI has a 3 approaches. One is expert based approach. Second one is intelligent based approach. Okay, expert based approach, intelligent based approach. Third one is learning based approach. That will go. Before going to that, you see this diagram. So many of you people now we are fond of data science. What is the data science and data analytics with respect to this artificial intelligence? See, this data analytics is a practice of using machine learning algorithms and visualization to derive insight. What is the difference between data analysis and analytics? Analysis is the process and analytics is making useful decisions or decisions. Whatever that your decision should improve company ROI. What is that ROI means? ROI, company ROI. What is the company ROI? Return of investment. ROI is nothing but return of investment. I'm investing this much. Now, how much I'm going to get in return? If your decisions, whatever the decision is able to improve this ROI, that we call as intelligent decision. Now see, the data science is the blend of data analytics and computer science and business domains. Now many places now data science and data analytics are using. What are the different types of data analytics? There are three types: descriptive, predictive, and prescriptive. What is the descriptive? Then describing about data, whether your data, because now we have two approaches. One is technology driven approach. Okay. Second one is data driven approach. Now previously we are more depending on technology, because technology has evolved. We are adopting the technology. Now technology is exhaustively using. Now we are much depending on data. Your data is a fuel for your ML models or AI models. So all this we call as a data driven approach. For example, you see that science of data driven decision making. So now that business analytics, whatever we take. Okay. So now this data driven approach, now you have to understand what is that analytics we are going to use. Data analytics. First analytics is descriptive. How to describe this bottle? What is the shape, color, texture and all? Now if your data may be text data, image data, audio data, video data, sensor data, first you have to get what type of data you are getting. You have to describe what is the nature of the data, what is the distribution of the data, all, what is the minimum value, maximum value, what is the mean value, what is the mode value, what is the skewness of the distribution, whether it is the distribution is skewed, left skewed, right skewed, or kurtosis it has. All these things you have to do. Now in latest we are using that EDA. In this EDA, what is that EDA? Exploratory data analysis. That we are doing everything, and pre-processing or removal, outliers, all that things we are doing in descriptive analytics. Second is a predictive analytics. What do you do in the predictive analytics? Predicting unknown value with help of known value. For example, you take any regression models or straight line equations. So regression models has same straight line. If it's change the straight line equation mx plus ce, okay, mx plus ce, then you can use same thing in regression model. What is that? Y equal to beta naught beta 1 x. Beta naught is nothing but c, and plus beta 1 x. Beta 1 x is the beta 1 is m and x. Okay, you know this beta naught and beta naught are the regressor coefficients. These are unknown. X and y are known. This we call as an historical data, previous data. From this previous data, we are going to estimate the values for this. Once you substitute these estimated values, then for any given mu x, you can predict this. Any, without knowing this beta naught beta 1, if you substitute x value, you cannot predict y. So now you substitute these values, and so from these two are known. Predicting unknown values with help of known values, that we call as a prediction. Now in machine learning we use a regression is a predictive model. There are two types of regressions, linear and non-linear. In linear, again we have simple linear regression, multiple linear regression, dummy regression, logistic regression, lasso regression, ridge regression, like that. If you have a time series data, we can use ARIMA model, S-ARIMA model. Even in Facebook, they developed a neural profit and all. So these are all predictive. If you go for deep learning, LSTM and a by-LSTM are a predictive model. What is the last type of, this one is prescriptive, is nothing but optimizing. You have to optimize. So how to remember these three types? Every day you are using in your life. For example, you go to a showroom to buy a dress, you are using this. What you will do first? You'll see whether my color is there or brand is there, what is the price. All these things are descriptive. Then you will take some dress and will go for wearing in a trial room. There what you will do, you will predict whether it is suitable for me or not. Then you come to the cash counter. At the time you will choose the dresses according to money is available. There you are optimizing. So these three type of analytics are part and participle of your all AI models. Whatever the AI models you choose, that one. Now we are living in an era of big data. I'll give only glimpse. Their big data has different characteristics: velocity, variety, volume. Because velocity is the speed of the data it is transferring. Variety is the type of data, form of data, structured, unstructured, semi-structured. Volume is size of the data. Not only that, we have data in doubts, veracity, data in open, or data in many values that we can use. These are the characteristics of the big data, right? Now, see this. Same big data we can use here. One application in smart healthcare, how they are using big data. Maybe this thing is not coming. Now we'll go to the third approach, learning approach. What is learning? Practice makes more perfect, and constructing or modifying what is being represented. This is very useful. Learning is making useful changes in your mind. How do you make useful changes? That sorry, what is learning? Now making useful changes in your mind, that you have to do. Okay, how we do that useful changes? First you have to set your mindset. If you are properly learned, then you can make a mission to learn. That's why mission learning refers to a system capable of autonomous acquisition and integration of the knowledge. Okay, what are the different types of mission learning? These are definitions I'm speaking. Different types of mission learning are three types. One is supervised learning, another unsupervised learning, reinforcement learning. When do you use supervised learning? When your data set has the labels. When your data has the labels, then you can use supervised learning. Now, fortunately, unfortunately, 80% of your data, 80% of your data is not labeled. 80% of your data is not labeled. At the time, what you'll do? You'll go to the unsupervised learning. Nowadays, we are not going to unsupervised learning. We are using a concept called as Gen AI. What is Gen AI? Generative AI. What is a generative AI? Now, I told you first AI has a different stages or types: narrow AI, general AI, super AI. AI has three approaches. What are the three approaches? Expert based, intelligent based, and learning based. Now AI has three tasks. What are the AI? Is a system capable of doing three tasks. What are the three tasks? First task is prediction. Prediction comes under this regression. Second task is classification. Third task is clustering. So third task. Okay, three tasks. AI has a three tasks. First task is AI is a system capable of doing prediction or classification or clustering. Now come to the generative AI. Generative is also a system capable of generating content. What is that content? That content may be text. Your content may be text or image or video or audio or anything. Now here what we need, if you go for supervised learning, either classification, what we require labeled data. We require to generate your labels with help of generative AI. Then we can use supervised learning. Okay, so there is one beautiful problem in a supervised learning. It's a classification. When do you say it is a good classifier? When classification error should be very, very minimal. Classification error, for example, we have three classes. One class here, second class, and third class. Okay, in another place, we have another class. If you take here, one class, second class, and third class. Now this class is good or this class is good? Always this is a good, because there is no overlapping. There is no classification error. So there are distinct classes. This one distinct class, this one is another distinct class. So whenever we are able to get this kind of distinct class, is a good classifier. So your main objective, when do you say it is a good classifier? When we have minimal classification error. You have to minimize that classification error such a way that your classes should be distinct. So what are all the different classifiers we have? Base classifiers. What is naive Bayes classifier, logistic regression, then ANN, artificial neural network, decision tree, SVM, KNN, all are base classifiers. So classification, in technically speaking, it is a problem. Classification is a problem. So these classifiers are tend to give bias results. So to avoid that bias, now the people are moving to ensemble classifiers. There are two types of ensemble classifiers. One is a bagging, other one is a boosting. In bagging is nothing but a bootstrap aggregating. That we use a random forest. Okay. In boosting, we have ADA boost, XGBoost and all, right? So these two models will avoid the bias and variance of variance occur in the base classifiers. So these bagging, okay, works in parallel, but in boosting work in sequential. Okay, in bagging if you use random forest, now you have a no flexibility to choose the base classifier. That base classifier should be decision tree, but whereas in boosting we have flexibility to choose any base classifiers, weak learners. Okay, so these will have the trade-off between variance and bias problem can be handled with the ensemble classifiers. Now while writing a research paper or publishing a paper, don't compare base classifiers with ensemble classifiers. For example, it's simple, base classifier is decision tree, ensemble classifier is random forest. Now in random forest we have number of trees. Now in the result, if you compare decision tree with random forest and tell that, and you get an inference random forest is performing well, it is obvious. That kind of things, if a reviewer sees in your paper, he'll immediately reject it, because that is obvious. We cannot compare one with many. Okay, so that things you have to keep in mind. Next one is unsupervised learning. We have clustering and partition based clustering, grid based, density based, depend upon grouping you do. Last type C, this reinforcement is very important. Nowadays, and for all real-time applications, we are using reinforcement learning only. For all your real-time applications, we are using reinforcement. See how reinforcement. Every day you are using reinforcement. For example, you take a Google Pay or GPay. First transaction you will get a reward. Okay. After some transactions, you will get a better luck for next time. So that is a penalty. Now whenever environment is unknown, that time use reinforcement. So agent will observe, select action using policy. If this action may have either you get based on your action, get a reward or penalty. Next time you will avoid that. You update the policy, learning policy, until you will get a good optimal policy. You will trade this. Now you see these three boxes. This is a descriptive analytics. This is a predictive analytics. This is a prescriptive analytics. So the data analytics is a part and participle of your machine learning models and deep learning models. Okay, so these are if you see this, you are able to watch this one. One application where we can use AI. Already AI in action. If you see, watch this video. So this is the slow in this. Now, same. Now, how do you convert? How to get into actions? Now, so far we have studied AI. In that, only one part we have studied, and three approaches. One is an expert, intelligent. Third approach only learning, mission learning. In this mission learning, how to get into actions? If I take a smart home, user activity recognition in smart home using a pattern clustering. Clustering comes under unsupervised learning. Temporal ANN algorithm comes under supervised learning. Now you are bringing into this concept into action. How you are bringing? Who are the users in a smart home? Father, mother, son, and daughter. Okay, what are their activities from morning to night? All that activities. How you convert that into actions? So this is a smart home environment. Now we are getting data into this. Okay, monitoring using sensors. That means now if you check that smart home, that video is available in YouTube also. Entire universe is going to ruled by sensors only. Entire universe is going to ruled by sensors. Now that data we are getting with a different type of sensors, then we are applying machine learning models, either supervised or unsupervised learning. So that we use the detection. You use the detection recognition, activity detection. What are their activities of users? Then activity model to make a decisions. That decisions are giving to caregiver, so that the entire environment of smart home is being controlled. How they are doing this? Say they are using hybrid models. You see this. This is the workflow of machine learning. What is that workflow? First they are getting a raw data, then doing pre-processing, then selecting which model, then validating and giving. Okay, there are 5 steps in any ML model. One is in a data collection, then data pre-processing, then model selection, model training, model evaluation, and last one is model deployment. So these now in the industry, they call it as MLOps. What is MLOps? Machine learning operations. Machine learning operations. So what they will do? They will check whether these models are perfectly working or not, or scalable or not. Right? All these operations now they are using in the form of MLOps. Previously we have DevOps. What is the development operations? Now they are using MLOps. Now they are bringing into AI ops. That means how AI operation can be done. So these 5 steps are very, very important. Up to evaluation we are doing, deployment we are not doing. While deployment into real time, we have to consider your model is lightweight or not, your model has a scalable or not, your model has compatibility or not. That things if you consider in deployment phase, then you can easily get it. Same AN and what we discussed in the previous slides. These are the different activities they taken. Taking bath, preparing breakfast, listening music, playing games. So now different machine learning models. Among this, ANN is giving good results. I'll take in 5 more minutes. Shall I continue up to 12:30? Sir? Hello? Sir? Shall I continue up to 12:30 or sir?
Yes,
What
sir,
is
you
time?
can continue.
Yeah. So up to this, we have seen machine learning. In this machine learning, these activities we are taking all are time dependent. See, this taking bath is a time dependent, preparing breakfast. If they change the time, then we have abnormal, right? Now, what is the different applications in the machine learning? We can identify the faces and expression, identify vocal patterns, identify credit card fraud detection and all. Now see this. So far we have seen one type of learning. What is that machine learning? Now this are able to classify what is a Labrador or fried chicken, able to classify puppy or labels, and a sheep dog and all, muffin and all. Okay, born owl or apple. So parrot and glaucoma, or raw chicken or Donald Trump. It is somewhat difficult to classify. Now see this Canadian cipher data, 10 classes we have, 10 categories. Test images we have 10,000. Training images we have 50,000. So which are human is better, or machine learning is better, or deep learning is better for this data? We were surprised. If deep learning is performing better than human. Deep learning is performing better than deep learning. That's why deep learning is performing better than deep learning. Sorry. Deep learning is performing better than the human. Human getting less accuracy when compared to deep learning. So how we'll see? What is exactly deep learning? Extending several layers of nodes between input and output. That we call as a deep learning. Why we extending number of hidden layers? Why we want to have several number of layers in between in input and output? When you extend number of hidden layers, you will go deeper and deeper. You extract the viable or useful patterns which are reason for your classification or prediction or clustering. So for doing that, you are extending number of. See this. Why deep learning becomes so popular? Because of, I told you previously, because of the GPU. Because of GPU is able to have net 8 into 10 to the power of 12 operations per second. Because it has this much, with a second, how many operations? Because GPU has inherently have massive parallelism. That's why this deep learning becomes so popular. We have computing power is available. Now see this, it is able to perform 27.1 times faster than your CPU. So that's why now people are going behind the deep learning models. So now this is a machine learning, one hidden layer, but whereas in deep learning we have what is the main exact difference between machine learning and deep learning? You see here, this slide. Now in machine learning, you have to extract the features separately. This person will do any kind of mistake, your prediction also go wrong. Now what deep learning is doing, feature extraction and classification, both model itself is performing. Okay, to extract the features, now your AI has become a very good tool to extract a viable features or important features, or which are reason for to do some classification or to do from clustering or do from prediction. So for that you are using very good deep learning. Okay, AI is an internally part of it to do. So what is the three models in deep learning? One is DNN, other one is CNN, other one is third one is an RNN. In DNN used for classification and forecasting of your model, deep neural network. But whereas widely used model for all your feature extractions and classification of images, we are using CNN. This CNN, convolution neural network, has three blocks. One is a convolution layer, other one is a pooling layer, then fully connected layer. In convolution, again we have three parts. One is a kernel or filters, then strides and padding. What is the purpose of a kernel or filters? This is a one filter or a kernel will move through entire image, similar patterns will extract. So now while you want to extract low level features, now you have to use low dimensional size of filters or kernels. You want to extract high level features from the image, you have to use high dimensional filter size or kernel size. So in that again you may get the doubt. So which dimensions? Odd dimensions we have to use or even dimensions. Most of the cases we are using odd the even odd dimensional filters or odd dimensional kernels. What is that 3 cross 3, 5 cross 5, 7 cross 7? Why we are using that? We can get a center point to compute. Okay. When you multiply your input image, intensity of input image are represented in the form of pixels. With the kernel, you will get a feature map. That feature map you are giving to pooling layer. The pooling layer is a downsampling. So whatever that pooling has a 3 types: maximum pool, min pool, or average pool. If you represent your image as an high level values wherever image is there, and low level values wherever image is not present, that time you have to use max pool. Otherwise we have to use min pool or average pool, depend upon your problem you have to choose. Okay, then fully connected layer is flattened layer. So this CNN model is a base model. Now people are using pre-trained model in CNN. What is that? Pre-trained models or transfer learning models are AlexNet, GoogleNet, ResNet, InceptionNet, all are pre-trained models. That can be very much useful nowadays. So you can utilize that model. That we call transfer learning model, because we need not to start from the scratch. It is enough if you change the upper layers. That means enough if you tune hyperparameters. What are the hyperparameters? Learning rate, batch size, epoch, all that things. So that if you do, it is a good, right? So now current trend is in the transformers. The transformers are giving 4 times better than your pre-trained models. Vision transformers. That is the latest trend in the deep learning. Okay. Similarly, recurring neural network. Now, in recurring neural network, used for sequence of items or language models or time series data. This recurring neural network has 2 problems. One is vanishing gradient and long-term dependency. To handle these 2 problems, they developed LSTM is a pre-trained model, long short-term memory that they are using. Okay. Now see the dependency. Data requirement for deep learning requires large data. For machine learning, lesser data. In accuracy, high accuracy, less accuracy. Time take longer time. This longer time only reduced from by using QPU, quantum processing. It requires hardware, GPU, here CPU. Hyperparameting, higher hyperparameter tuning can be done. Okay, these are some of the packages we are using, Python packages, PyTorch, TensorFlow, and scikit-learner and all, right? Now these are now how this will work. Different activation function. For example, you take this input you are giving. Now you are getting output in deep neural network. Now see that input data we are passing. We are getting 0. But actually the value is 0 class. But we are getting 0.7. 0.7. Now what you have to do? We have to compare the target output. We have to reduce the output. So for that we are randomly adjust your weights till your get. So how we adjust that? Repeat this 1,000, maybe million times, each time taking random training expense. That we are. Okay, that way model will work. Now see this. Which one is better? Human getting 94%, whereas your machine learning 80%. See that deep CNN. So now it is overcoming. It is better than a human performance. That's why people are more going for deep learning models. So this is the convolution layer. Already I explained it. Filters, right? This filters work and how it will come. Max pooling layer. So that is a downsampling. What is the maximum value? 6. Here maximum value 8. Maximum value 3. Maximum value 4. So that will work, right? A full dropout can be avoid the overfitting and all. Fully connected layers. These are the some layers. Okay, next see here. What is the generative AI? What is generative AI is used to generate the content. What are the different models are there? You see, GAN model and variational encoders and transformers, RNN are generative. Diffusion models, large language models, all are generative models. Now RAG models, all are generative. In this first model is generative adversarial network. So there we have two things. One is a generator, other one is a discriminator. What is the purpose of generator? It will generate the content. And discriminator, it will verify whether the content is, whatever content is generated, whatever the fake data is generated or synthetic data generated is correct or not with respect to real data. Till that this process is going, right? It will generate, it will verify. Like the teacher and student. Teacher will write exam, student will write exam, teacher will correct that exam. Okay. Till student write correct answer, teacher will train. Similarly, this. Yeah. Similarly, variational encoder, decoders. These are the two important models. Okay. Now, this now this is a reality now. What is the reality? Now this. With deep learning, big data, GPU. Why so much of success now? AI and computer vision, a reality in today's world. Reality in today's world. The combination of your big data with deep learning models and hardware GPU come into reality. Now see this small video. Already it is in the market. It is a already it is in market. If the time permits, I will show another one or I will stop. Here you see, this can be all these are different applications. Let's see this video. Is this an already Amazon? See Amazon Go how it is working. Now there's no checkout, no lines. That video I will play and I will stop. The last video I will show how. Right? I will summarize. This video is there in a YouTube. You can go through. So I'll summarize what we discussed today. Now we start with an AI. What is AI? Making intelligent missions, or it's nothing but an artificial intelligence or man-made intelligence. Where this intelligent got? So this intelligent we got it from mimicking human senses. What are the human five senses? eyes, ears, nose, and tongue, touch, right? So from that computer vision, knows and all. What are the different stages of AI? One is a narrow AI, general AI, super AI. From that, what we got it? Now, different approaches of AI. Expert-based approach, intelligent-based approach, learning-based approach. In learning, we have seen, intelligent, we have seen different ANN, genetic algorithm, ASO, PSO, and fuzzy logic. And in learning, we did 3 learning approaches. First is machine learning. In that machine learning, again 3 types: supervised, unsupervised, reinforcement learning. And what is the task of artificial intelligence is to classify or predict or cluster. Okay. Then from that we move to the deep learning. In deep learning, again 3 models we have seen: DNN, CNN, RNN. And so these, what are the functionalities of each one? Then we move to the transfer learning, and federative learning also is there. Okay. Then generative AI 2 models. Some applications where we have seen one is a smart home, other one is an AI flow detector, and Amazon Go. Like that, so many applications are there. Now you can take up any problem and you can work it out. Okay. Thank you. Thanks for the opportunity. Thank you. Sir.
Thank you so much, sir, for your enriching and highly engaging keynote session. We now open the floor for questions from the audience. If you have any questions for the speaker, please feel free to raise your hand.
Hello. Good morning, sir. I have a question. With the rise of powerful models like GPT, do you think
Yes.
deep learning is moving towards general
Yeah,
intelligence
tell
or
me.
recognition patterns?
Inside your chat GPT is that generative pre-trained transformers. Generative pre-trained transformers. Inside the transformers, your multi-layer perceptron are working. Okay. Now they have channel attention mechanism. So now that in transformers, your deep learning is a part and participle of it.
Yes, sir. Thank you.
How can we bridge the gap between data hungry deep learning models with real world domains with limited data availability?
Yeah, good question, right? Because now one of the major problem for your deep learning models is data scarcity. Okay. How we can get nowadays, getting a real data is a difficult task. For that, now you can use generative AI to generate synthetic data, to generate the synthetic data which will look like real data. Okay, all many generative AI models are now used for generating and solving the problem of data scarcity or data hungry. Okay, for that they are using now generative. GAN models are using, variational autoencoders are using, many are using to generate your data.
Hello, sir.
You got it?
Yes, sir. I have another question, sir. The question is,
Yeah.
in your opinion, where do you think we should draw the ethical line when considering deep learning in surveillance, healthcare, and hiring?
Where do?
Where do we draw the ethical line when drawing? Where do we draw the ethical line for taking deep learning
Yeah,
into these domains?
very good question. Because ethical AI now into, yeah, very good. Now ethical AI, now they are using ethical AI. How do you secure your data? The privacy, right? For example, your medical, how do you not data breaches, data leaking happening? For that, they are using a cyber security mechanism and data security. Okay, you have to have ethical things. Now the generative AI also you can use in offensive way or defensive way. We can try to incorporate defensive mechanism. That means you have to use your either deep learning models or generative AI in an ethical way. For that, government of India is devising certain rules and policies for data privacy, data privacy, and securing your data. Your model, when you go, if you get into real time, your model should satisfy the conditions and rules are framed by government of India data that ethics. That if it's satisfied, then only it will come into real model. Got that point?
Yes, sir.
Good afternoon, sir. Can deep
Any
learning
other?
truly understand our language, or it
Good
can?
afternoon. Deep learning is yeah. Deep learning is
Learning truly understand our language, or it is just good at mimicking it?
deep learning is truly understand. See, now if you say working principles, it is a black box test only. Black box. Whatever inside it is happening, how your weights are adjusting, that nobody is known. How that working mechanism, it is only with a trial and error only it is working. That's why people now moving from that to explainable AI. Explainable AI. What is happening in that process? For example, I told you, ANN has the 3 layers. One is an input layer, the output layer. In between, it is not a process layer. It is hidden layer. Because what is happening inside that model, nobody knows. That's why people are moving now to explainable AI, where they can explain the process of how this thing happens.
Thank you so much, sir, for your enriching and highly engaging keynote session. Your talk on AI in action, real world applications for engineers, beautifully showcased the practical power of artificial intelligence in solving real world problems across diverse domains. This session was perfect blend of technical depth and application relevance, making it immensely valuable for our student and academic community. Your journey, expertise, and dedication to impactful research truly inspired us all. Even though session was held virtually, your words and presence created a lasting impact. Thank you once again, sir, for joining us and sharing your expertise with us today, sir.
Thank you. Thank you all the participants, and thank you organizers for giving this opportunity. If it had been physical mode, it would be interactive. I'm happy students are participated and asked some queries. Now, this is the one session where I'm truly happy of your questions. Many sessions, virtual sessions, may not have any questions. But here, I'm so happy to answer your queries. And thanks for the organizers, and thanks for the invitation. Special thanks to Brahmanandam Reddy sir, who, baby madam, who has invited me. Thank you.
Thank you, sir. Thank you everyone for attending today's session. You may now leave to your classrooms.